Welcome to Statistics for Artificial Intelligence, Lecture 1, PhDAI730. This is Professor T. Freed Muhammad, and let's get started in the learning together. So we are to revisit the concepts of statistics used in artificial intelligence in quite depth in this lecture. The learning begins this week. We will explore the foundational concepts of central tendency and measure of dispersion, which are essential for understanding data distribution and variability. In the realm of artificial intelligence, these statistical measures are crucial for pre-processing data, training models, and evaluating their performance. Central tendency helps artificial intelligence algorithms identify the central values in datasets, which is vital for making predictions and classifications. Measures of dispersion, on the other hand, provide insights into the spread of data, aiding in the detection of anomalies and assessment of model accuracy. Using Python, a popular programming language as we all know in the artificial intelligence domain, we will perform calculations and visualizations to deepen our understanding of these concepts. Python libraries such as NumPy and Pandas will be instrumental in handling data, while Matplotlib and Seaborn will help us create insightful visualizations. Why statistics in artificial intelligence? That's a great question. Let's look into this with more detail. Artificial intelligence systems fundamentally learn from data, drawing patterns and insights that enable them to make decisions and predictions in complex, real-world environments. A quintessential example of this is the self-driving car, which does not operate on hard-coded rules for every possible scenario, but rather learns from massive datasets of driving experiences. These datasets comprise millions of miles of video footage from cameras, LiDAR points, clouds, radar readings, and sensor fusion data, all meticulously annotated with information about pedestrians, road signs, lane markings, and other vehicles. By analyzing this data, cars' underlying machine learning models, often deep neural networks, in reality, we apply deep neural networks for this entire data set to learn to recognize objects, understand context, and predict the behavior of other road users, forming a probabilistic understanding of the driving world. The learning process transforms raw sensory data into actionable intelligence, for instance, by processing countless examples of what a stop sign looks like from different angles in various weather conditions. And when partially obscured, the system learns a generalized representation of a stop sign. It does not just memorize specific images, it learns the essential features that defines one. Similarly, by analyzing trajectories of pedestrians, the model learns to anticipate likely paths, distinguishing between someone standing on a curb and someone beginning to step into the street. This ability to generalize from examples is what allows the artificial intelligence to handle the infinite variability of real-world driving, navigating situations it has never encountered in exactly the same form within its training data. Ultimately, the performance and safety of self-driving car are directly tied to the quality, quantity, and diversity of the data it has learned from. Statistical measures of central tendency and dispersion are crucial in this pipeline, helping engineers understand and pre-process this data, for example, analyzing the typical central tendency and the variability, which is dispersion of sensor readings, under different conditions can identify calibration errors or detect anomalous sensor behavior by rigorously applying these statistical foundations. Developers can create more robust models, ensure the training data represents the real world's inherent randomness, and build AI systems that reliably translate data into safe, intelligent navigation. Data distributions. Now let's look into answering what is our distribution. A foundational concept in both statistics and artificial intelligence is the data distribution, which describes how values or outcomes are spread across a dataset. In healthcare area in specific, understanding distributions is not just academic. It can be a matter of life and death. Consider a hospital monitoring the resting heart rate of its patients. A simple average might suggest a typical rate of 75 beats per minute or BPM. However, the distribution of this data tells a far richer story. Is it right? Bell-shaped curve clustered around 75 BPM, indicating a generally healthy cohort, or is it a wide flat spread from 50 to 110 BPM, revealing a mix of highly fit athletes and patients with potential cardiac issues? This shape of spread of data fundamentally changes clinics' interpretation and directly informs which AI models are appropriate for analysis, as different algorithms make different assumptions about the underlying data distribution. The power of analyzing distributions become especially clear in medical diagnostics and artificial intelligence division. It's technically AI driven risk prediction. For instance, when developing an algorithm to detect diabetes by analyzing blood glucose levels, researchers don't just look at a single glucose value. They examine the entire distribution of glucose readiness across thousands of patients, both healthy and diabetic. They might find that the distribution for healthy patients is roughly normal, centered around 100 mg, while the distribution for diabetic patients is bimodal, showing peaks at both moderately elevated and severely elevated levels. An AI model trained to recognize these distinct distribution patterns can then assess a new patient's likelihood of having a disease not just by single test but by evaluating where their profile fit within these probability landscapes, leading to more accurate and nuanced diagnosis. Leveraging and understanding of data distributions allows healthcare AI to move beyond simplistic averages and toward personalized probabilistic medicine. In predictive analytics for hospital readmissions, for example, model analyze the distribution of key variables like a patient's age, number of prior admissions, and lab results to identify which patients fall in the high risk tail of the distribution. This enables targeted interventions. Furthermore, monitoring shifts in the distribution of vital signs in an ICU patient's population over time can serve as an early warning system for emerging hospital acquired infections or sepsis outbreaks. Hopefully, this has given you some understanding of the data distribution's utilization in the area or the arena of healthcare. Now, let's go to the next slide and see what we have to learn there. The center of data, also known as the main idea in any given area of the industry where we are dealing with, and what we are dealing with, and what are the possible predictions or probable predictions or plausible predictions. The concept of the center of data provides a crucial reference point for understanding a dataset's typical value, a function vital to AI systems. We carry on working with the healthcare example. Identifying this center helps establish clinical baselines and norms. For example, when analyzing the systolic blood pressure readings from a population to train a diagnostic model, simply calculating the arithmetic mean might yield a value of 120 mmHg. This single number gives a quick summary, a view of the population's central tendency. However, this average can be misleading if the data includes extreme outliers such as readings from patients and hypertensive crisis. The mean would be pulled upward, no longer representing the typical patient. A more robust measures like the median, which finds the middle value, would be less affected by these extremes and could provide a more reliable central reference for what constitutes a normal range in the specific cohort. Selecting the correct measure of the center directly impacts the performance and fairness of AI models in medicine. A predictive algorithm for patient length of stay in a hospital might use the mean historical stay to allocate resources. If the data is skewed by a few patients with exceptionally long stays, the mean would overestimate the typical duration, leading to inefficient planning. Using the median would create more accurate operational baseline for categorical data such as most common post-operative complication on a surgical ward. The mode identifies the central tendency, and AI system flagging frequent complications would prioritize the model outcome, enabling staff to focus preventive measures effectively. Therefore, correctly defining the statistical center is not merely the technical step. It ensures AI tools are built on an accurate and representative understanding of reality, forming a reliable foundation for clinical decision support. Now let's look into the mean or the arithmetic average in a little bit more depth. The mean or arithmetic average serves as a foundational statistical tool for forecasting demand and optimization operations. We are looking into an inventory control such as Walmart, Sam's Club, Costco, etc., or Target. So in the context of inventory control for a big box store, the mean provides a simple but powerful estimate of expected sales. By calculating the average weekly sales of a product like gallons of a specific paint color over a past period, managers establish a reliable baseline. This average consumption rate helps determine routine reorder points and quantities, ensuring shelves are stocked to meet typical customer demand without constant manual review. The mean transforms historical sales data from a chaotic list of numbers into a single actionable figure that drives the replenishment cycle. Applying the mean effectively allows for significant efficiency gains in supply chain management. For seasonal items such as patio furniture, a store might calculate the mean monthly sales during the summer season to plan its initial seasonal purchase. The central estimate helps ensure and secure appropriate bulk orders from suppliers and allocate warehouse space. By comparing the current week's sales to the historical mean, automated systems can flag unusual activity. A significant dip might indicate a stocking problem, while a sustained increase could signal a rising trend. prompting an order adjustment. Relying on the mean for these core calculations create creates a stable data-driven inventory systems that minimizes both excess stocks and costly storage as well as shortages. Hopes this makes sense. And the code is given here: import numpy as np, data as 246810. The mean value is np.mean data, and it'll give you the answer. So you're most welcome to test run this for your base understanding. The middle value. And let's look into this with an example. We'll carry on working with the inventory control example here. The middle value or median provides a different and often more resilient perspective on central tendency by identifying the point where half the data falls above and half below. In inventory control for a big box store, as we have been discussing this previously, this measure is crucial for managing products with erratic sales patterns or those susceptible to extreme outliers. Consider the sales data for a high-end appliance such as luxury refrigerator. While the store may sell very few units most weeks, a single large promotional event could result in a week with 10 times the normal volume. The arithmetic mean of these sales would be skewed upward by this outlier, suggesting a consistently higher demand that does not exist. This inflated average could lead to overstocking and capital being tied up in slow-moving inventory. Using the median sales figures offers a safeguard against this distortion. By focusing on the middle value in a sorted list of weekly sales, the inventory manager finds the typical sales volume that is not influenced by those rare extreme weeks. This provides a more realistic baseline for determining the minimum stock levels and reorder points. For products with volatile demand, setting inventory policy based on the median ensures the store maintains a buffer for normal operations without overreacting to typical sales spikes. This leads to a more stable and cost-effective inventory system, optimizing both storage space and working capital. The most frequent value. Let's look into this using the same inventory control arena. This is also known as mode. The mode identifies the most commonly occurring data point in a set. In inventory control for a big box store, as we are discussing in this current lecture, this measure is particularly useful for managing products with distinct popular preferences that dominate sales. For instance, when stocking a basic item like white cotton t-shirts, sales data may show that size medium is purchased far more often than any other size. The mode clearly identifies the size as a peak of demand. Knowing this most frequent value permits managers to prioritize and optimize stock levels for the best-selling variant, ensuring the highest turnover and customer satisfaction for the specific item. This focus on the model value streamlines operations and purchasing decisions. By analyzing sales data, a store might find that the most frequent purchase of light bulbs is a specific 60-watt LED model. This insight directs purchasing managers to allocate more shelf space and maintain a large safety stock for the exact model compared to less popular alternatives. The mode provides clear, actionable intelligence about consumer behavior, enabling a store to meet the majority of customer demand efficiently. This strategy reduces the risk of stockouts on high volume items and simplifies inventory forecasting for standardizing products. Comparing mean, median, and mode. The skewness affects which measure best represents typical value. Let's look into this in more depth with an example. In artificial intelligence, the choice between mean, median, and mode is dictated by the nature of the data and the specific modeling goal. The mean is the cornerstone of many foundational artificial intelligence algorithms, as discussed earlier, such as linear regression, where it is used to calculate loss function like mean squared error or MSE. However, its sensitivity to extreme values can destabilize a model trained on skewed or outlier ridden data. Conversely, the median offers robustness, making it indispensable for tasks like anomaly detection or creating tree-based models, where splitting data at a median can minimize error from outliers. The mode is unequally or uniquely valuable for categorical data, driving classification algorithms and recommendation systems by identifying the most frequent class or user preference. Skewness fundamentally determines which measure best represents a typical value because it describes the asymmetry of the data distribution. In a symmetric bell-shaped distribution, the mean, median, and mode are approximately equal, making the mean a reliable and information-rich summary. When data is skewed right with a long tail of high values, the mean is pulled upward toward the tail, while the median remains closer to bulk of the data. For instance, in modeling user income on a platform, the mean might be inflated by a few billionaires, misrepresenting a typical user. The median income provides a more accurate central reference. Therefore, in skewed distributions, the median offer becomes the superior measure of central tendency, as it resists distortion and better reflects the experience of a typical data point, leading to more robust and interpretable AI models. When to use each measure in artificial intelligence? Now, that's a very good question. Now, let's switch gears and bring in robotics. So, in the arena of robotics, the selection of mean, median, and mode is dictated by the specific data types and operational context. The mean is essential for calibrating precision systems and sensor fusion, where averaging continuous data like positional error or noisy sensor readings provide the most likely state estimate for smooth control. The median is critical for robust perception in the unstructured environments, as it disregards outliers from corrupted LiDAR scans or erratic sensor data, ensuring safe navigation and decision making. And the mode applies to categorical decision making, such as interpreting the most frequent classified human command or achieving consensus in multi-robotic voting systems, thereby stabilizing high-level logical functions and bridging perception with discrete reliable actions. And now we jump into the arena of dispersion, using robotics as our main understanding. Whereas in the selected slide, the analogy is two basketball players with same average points but different consistency. So rather using robotics, let's use the same analogy given in this to understand dispersion in a little bit more depth. In sports analytics, measure of dispersion reveal the critical story behind identical averages, as illustrated by two basketball players, Alex and Jordan, for example, who both averaged 20 points per game, while the mean indicates equal offensive contribution. Alex's low average or low range and standard deviation show his scores are tightly clustered around 20, marking him as a model of predictable output, whereas Jordan's high range and standard deviation reveals widely scattered performances, making him a volatile, high risk player. This distinction between consistency and variability is paramount in artificial intelligence, where a model with low variance in its predictions is reliable and trustworthy for deployment, even if its average accuracy matches a more erratic model, proving that the average tells you what to expect, but the dispersion tells you how much to trust it. Now let's look into range in a little bit more depth. This provides a quick snapshot of variability by calculating the differences between maximum and minimum values. As shown by the two basketball players with identical 20-point averages, or as we discussed, Alex's narrow 10-point range from 15 to 25 points signal consistency, while Jordan's vast 30-point range from 5 to 35 points reveal high volatility that their shared average conceals. However, this measure is limited because it is defined solely by two extreme values. A single anomalous game disproportionately shapes the range without describing typical variation, making it a useful prompt for further investigation, but necessitating more nuanced metrics like standard deviation to fully quantify consistency. And the Python code is given for you to look at. Variance. This is average standard deviation. Variance quantifies the typical squared deviation from the mean, moving beyond simple range to precisely measure consistency, as illustrated earlier by the two basketball players with identical 20-point averages. Alex's low variance confirms his scores are tightly clustered, signaling stable and predictable performance, whereas Jordan's high variance, amplified by squaring large deviations from outliers like 5 or 35-point games, statistically captures his explosive volatility and the unreliability of his average. In artificial intelligence, this metric is a key diagnostic. A model with high variance is often overfit, learning noise along with signal and performing erratically on new data, making understanding variance essential for distinguishing reliable low variance performers from volatile ones in both sports, analytics, and machine learning simultaneously. Now let's look into standard deviation, the most common measure. The most common measure translates theoretical variance into an interpretable real-world scale, making it indispensable in robotics arena. And this is where we are now discussing robotics, for quantifying precision and reliability, such as when measuring a robotic arm's repeatability, where a low standard deviation in positional error confirms high precision in a tight cluster around its target. For autonomous perception, the standard deviation of LiDAR distances readings directly assesses stability, with a low value enabling smooth control and a spiking value serving as an immediate alert for sensor noise or environmental interference. Consequently, by precisely measuring the expected magnitude of variation in critical signals like joint torque or classification scores, standard deviation acts as a core diagnostic tool for system health, permitting robotics or roboticists to ensure actions are based on consistent data, predict failures, and build robust, predictable autonomous systems. Now let's look into interquartile range, a robust measure that we use in the industry. Let us continue the robotics example. The interquartile range or IQR serves as a critical robust statistical tool for managing the noisy and often erratic data from real world sensors. It is calculated as the difference between the third quartile or Q3 and the first quartile or Q1, effectively capturing the spread of the central 50% of the sensor readings while ignoring extreme values. This makes it indispensable for perception systems such as robot using the depth camera or LiDAR, where spurious readings from glare or reflective surfaces are common. By focusing on IQR, the robot can filter out these outliers to obtain a reliable estimate of distances or object positions. The IQR resistance to distortion is leveraged for real-time anomaly detection and system health monitoring by establishing fences at Q1 minus 1.5 multiplied by IQR and Q3 plus 1.5 multiplied by IQR. A robot can flag sensor malfunctions or unexpected environmental obstacles as mild anomalies, while thresholds at 3 multiplied by IQR can identify critical sensor failures. This allows an autonomous system to dynamically adjust its confidence in the data stream, perhaps by downweighting a faulty sensor or triggering a safe stop procedure, thereby maintaining operational safety and reliability in unpredictable conditions. Now let's look into coefficient of variation in a little bit more depth. The relative dispersion or the coefficient of variation CV is calculated as standard deviation divided by mean multiplied by 100%. Is a standardized dimensionless measure of relative dispersion that enables the direct comparison of variability across datasets with different units or means, such as comparing two stocks where stock A mean return is 10%, standard deviation is 2%, has a coefficient of variation of 20%, and stock B mean return is 20% and standard deviation is 6%, has a coefficient of variation of 30%, revealing the stock A is relatively less volatile per unit as expected return. In data science and artificial intelligence, the CV or coefficient of variation is invaluable for feature analysis and model diagnostics, as a high CV can indicate noisy and sparse data that may need transformation, while a low CV may signal a feature with little informational value, permitting practitioners to prioritize inputs, assess sensor reliability in systems like robotics, and compare model performance stability across different scales for more robust outcomes. So the AI applications on using all these measures, let's look into this in a little bit more depth. Data pre-processing. Many algorithms assume standardized data. Outliers can skew model training. Features with different scales cause bias. The common techniques are standardization, with X is minus mean divided by standard deviation. Creates mean is equal to 0, and so standard deviation is 1. Normalization, the formula is given. The robust scaling, the formula is given. So from sklearn or pre-processing, import standard scaler, robust scaler, and then you can apply that to apply on your data frame, and that'll give you the data pre-processing, that how it works in depth. Anomaly detection is another arena that artificial intelligence is very good at, using the z-score method, the interquartile range method, the modified z-score. And the real world use cases are fraud detection in transactions, in a credit card or in a mortgage, fault detection in manufacturing, and network intrusion detection. I would suggest you to look into the anomaly detection and find some research papers available on Google Scholar or the ACM, Association of Computing Machinery, or IEEE Explorer. This will allow you to understand more of such in depth. The model evaluation is another arena that I strongly suggest you to read some research papers. The performance matrix using central and dispersion is mean absolute error, or MAE, average absolute difference, root mean squared error, RMSE, square root of average square differences, sensitive to outliers, R square score, proportion of variance explained. So I suggest you to look into these by conducting a little bit more research, as mentioned earlier in Google Scholar. And there are openly available research papers that you can download and read. The choosing matrix is another area where we use median based matrix if outliers concern, use mean based matrix for normally distributed errors. So I strongly suggest you to conduct a little bit of research in these areas. So let's conclude this lecture. We have explored the foundational concepts of central tendency and measure of dispersion, which are essential for understanding data distributions and variability. In the realm of artificial intelligence, these statistical measures are crucial for pre-processing data, training models, and evaluating their performance. We also looked at Python libraries such as NumPy and Pandas. These will be instrumental in handling data, while Matplotlib and Seaborn will help us create insightful visualizations. Happy learning. See you in the next lecture.